All right, thank you so much for inviting me. It's really great to see that so many people have turned out for an event like this. I'm glad to see that these are taking place and you can get such a great set of other speakers. It's great to see the work on omnidirectional vision right before this. So the work I'm going to talk about today is joint work with my PhD student, Daniel Gang, and a master's student in my group, Aaron Park. And I think a lot of us have been kind of blown away over the last few years by the abilities of these diffusion models to create really compelling images. For those who maybe haven't seen it, you can generate really, really impressive images just from a single text prompt. And these images often range from being photorealistic to almost any style you might imagine. And we wanted to see maybe if we could take this idea even further. Is it possible to generate maybe some of the edge cases in images? Like, for example, you can consider perceptual illusions. For example, this is an image by Salvador Dalli, and at first glance, it might have one perspective, but then if you view it a different way by rotating it, you'll see something completely different. These sorts of multi-view optical illusions have a long history. For example, in 1590, this looks like a fruit basket. When then you rotate it, you look carefully, it's also has an interpretation as a face. And so we wanted to see if it's possible to generate multi-view optical illusions like these. And is it possible to use the same techniques to kind of handle this edge case of perception? Now, of course, the illusions have a long history in computer vision. So we're also interested in this from a scientific perspective. For example, visual illusions are often used to probe human perception. Famous examples include checker shadow illusion, where you create an image that has a certain interpretation to human, and due to the way that we perceive the lighting and shadows, or the famous hybrid images of Odoliva. These are images that have a different appearance depending on the distance that you view them from. This image here looks like Albert Einstein from one perspective, and then from another or different distance, it will look like Marilyn Monroe. And these are examples where these optical illusions are used to try to understand how humans perceive the world. There's also a lot of cases where we can use optical illusions to probe machine perception as well. A really famous example of this are adversarial examples. If you create an image that you can, there's a famously result that shows that you can trick neural networks into having a different interpretation of an image than a human would. And that is being used in a way to indicate that perhaps the way that these classifiers are interpreting these images don't exactly match how humans perceive them. And maybe most relevantly, some really interesting recent work that kind of probes how classifiers that are based on diffusion perceive the world, and how they seemingly can fall for some of the same optical illusions as humans. So those are some scientific reasons why I think it's really important to study optical illusions, but mostly we're interested in just creating these illusions for fun. And you might, as a first attempt to this, you might just go out and try to collect a whole bunch of supervised training data. Unfortunately, I suspect that there isn't enough data out there. There aren't that many examples of images that have these different interpretations. You'd also need to have like the corresponding text prompts to prompt the model to create them, to be able to tell, this is a sketch of a dog, but from a different perspective, it's a sketch of a rabbit. And you need to have a way to define the different views of the image that the model would be perceiving it through, like, for example, how to rotate it. And so instead of doing this by explicitly training a model to solve the task, what if instead we just try to take an existing text-to-image diffusion model and we manipulate it to allow it to create these perceptual illusions. And we'll do everything just at inference time using an off-the-shelf, already trained model. And just for those who maybe haven't seen it before, diffusion models generate images by iteratively removing noise from initial image that's just all noise. So we might start with this image on the left that's just entirely Gaussian noise, and we'll just iteratively remove noise, and eventually the model will essentially hallucinate an image from that noise after enough iterations. And so what if we use this strategy to create perceptual illusions? We'll make one small modification to this pipeline. We'll start with our noisy image, and then we'll denoise it as usual. But we'll also separately look at this image from a different view, say a rotation. And we'll denoise that rotated version of the image using a different text prompt. Both of these images, when passed through the diffusion model, will have an estimate of the noise at this iteration. And we'll just average these two noise vectors together after undoing the view transformation that we performed. So if you were to just look at the top section of this figure, it would just be the standard reverse diffusion process that you would have seen in an ordinary diffusion model. The difference is we have the second step that's going on that's estimating the noise from a flipped version of the image, and we're just averaging those two estimates of the noise together. Then just like in standard diffusion, once we've estimated the noise, we can go back and remove that noise from the image by just subtracting. And here's the result. This is an image. From one perspective, it looks like an oil painting of people around a campfire. But if we flip it upside down, we see an oil painting of an old man. And we've tried this on a lot of other images. I'll show you some more examples in a second. But what I want to point out is it's a very, very simple method. We're essentially taking our noisy image, processing it with multiple views, each of which we're representing here as a function of vi. We're estimating the noise from each view. We're undoing the transformation, then averaging those estimated noise vectors together. Here's another example, a drawing of a giraffe from one perspective, and from another, it looks like a penguin. Oil painting of a ship. And from another perspective, we see an oil painting of a bird. For those who maybe don't see it, the eye is right here. The body of the bird is there. And this is an example of a type of illusion that has already existed in prior work, where you can take a word and rotate it and see the word again from this other rotated perspective. So here we see the word blessing in both of these views. Another one, oil painting, a snowy mountain village, and rotated. It looks like an oil painting of a horse. For those who don't see it, the eyes of the horse are here. The snout of the horse is here, and so on. And we can also try to come up with other views besides simple rotations. So what if instead we use a center rotation? We'll rotate just the center of the image, and we can make that pop art image of Albert Einstein look like a pop art image of Marilyn Monroe. All right, I would just take a moment. Are there any questions? Okay, great. So those are cases where it seems to have worked successfully. We can create these rotated. Oh, wait, sorry. I see there's a Q&A. Okay, the question is, I'm having trouble getting my prompts to do exactly what I need them to do. For example, I need a guy named Sam standing in the army uniform. Yeah, maybe I can answer that first question after, because it seems to be kind of a general question about image generation. I think it is quite hard to prompt these models, and I consider this to be a really important ongoing issue with them. Another question is, how much data is needed to train this kind of diffusion model? That's a great question. We're using a model called Deep Floyd. It's an open, sort of open model by I believe by Stability AI, that it's kind of unique in that it's a pixel diffusion model. It's not based on latent diffusion. And I believe it was probably trained on, like, I don't remember exactly what it was trained on, but it's likely to be something like the Lion data set, which is billions of images. So there's really a lot of training data that's going into these recent methods. But I think also it's very important to have, increasingly becoming clear, it's important to have very high quality training data as well. How do you create a deception illusion picture using just prompts instead of taking perfection illusion image as a reference? Yeah, so yeah, in this case, this model, I mean, presumably it's seen some optical illusions during training. These models have essentially seen the whole internet in their training set, so it probably knows something about illusions, but very likely the way that it's knowing about the illusions is due to this this inference time trick that we're doing, where we're denoising a noisy image in multiple ways. Could you see this method as a way to edit images via prompts? Yeah, that's interesting. I think there are definitely ways you could adapt the underlying techniques to do image editing. In this case, we use them to do specifically to make illusions, but I think these sort of inference time tricks where you take the noisy image and you like manipulate it and denoise it, use it in multiple times. There's a lot of techniques that kind of have that flavor, and this is one particular instance of it. And techniques like SD edit, for example, are very much along the same lines. Let's see. So you're interested. Someone says they're interested in applying these dual images for some of the art. Yes. In fact, there's a Jupyter notebook on the website you can use to try this out. I'll have a link at the very end of the talk. But you can also just go to my website and you can check it out. Somebody very kindly also made a hugging face space for it, which maybe we probably should link to on our website. But there's one of those floating around, and if you'd like an easier interface, you can use that as well. The question about training from scratch, actually, there's no training here. We're just using an existing pre-trained diffusion model, and our entire method is just these tricks that we perform at test time. I don't know how many parameters they have. It's a lot. Yeah, so maybe I can't remember offhand, but yeah, it's quite a lot. These are very large, fairly large models. They're not nearly at the level of the language models we've been seeing, but they're kind of increasingly becoming larger and larger. Yeah. So one of the questions about the applications, I'm not sure. I think for us it was kind of the curiosity-driven science rather than a particular application of illusions. Though I do think there are ways where it's useful to have images that have different perspectives, like images that get interpreted in multiple ways from different angles or from different views. I think that can be useful in general, but our main drive was really just to see if it was possible to do this and to try to make interesting images and see how far we could push these diffusion models. And finally, yes, we have to provide the view, this function v, in order to determine what the other view of the image will be. And so we have to indicate what the direction is that way. Okay, great. So thanks for all the wonderful questions. I'll stop again later to answer the rest of the questions you have. Okay, so I showed some examples where this works. There's also, interestingly, some examples where it really almost catastrophically failed. And I want to show those because I think they kind of help us understand why the method is or isn't working. For example, this is what happened if instead of rotating the center by 90 degrees, we rotated by 135 degrees, like a number that wasn't a nice round number. And we got this image that really looks neither like Albert Einstein or Marilyn Monroe, and it looks really, really incorrect. There's lots of saturated pixels and so on. And we also tried making hybrid images using this approach. We tried to make an image such that if you downsample the image, it would have a different interpretation. Again, totally failed. Neither of these perspectives really looks like Albert Einstein or Marilyn Monroe. So what's going on? Why is it that some of these illusions worked really well and others completely failed? Well, we thought about it, and one of the issues is that these diffusion models are very particular about their inputs. They're trained to denoise images, and the amount of noise in an image at iteration t is a very, very particular amount of noise. And also the image itself is scaled. So over time, you're kind of scaling the image such that you eventually end up entirely with noise. And so that means that in order for us to satisfy the preconditions of what this diffusion model could work with, our input better have these exact same statistics. It ought to be an image with a particular weight attached to it and a noise with a particular standard deviation. And the noise also, importantly, has to be just an IID standard Gaussian, because that's what these diffusion models have been trained on. And so if you consider what happens when you apply this view function v to the image, we have to get a new image that satisfies these properties. It's still an image with a particular amount of noise and a particular scaling. And so these constraints together suggest that one particular view that should be really useful is a linear transformation. Suppose that we take our image and multiply it by a linear transformation A. A matrix A that kind of indicates the linear transformation. Well, if we do that, we see that due to the properties of linearity, this will result in a new image that's a weighted combination of the matrix multiplied version of the input image plus the noise multiplied by that same matrix. And that's nice because there are certain types of linear transformations that when you multiply them with the noise vector will result in IID Gaussian noise. And in particular, if your transformation is an orthogonal transformation, then you're not going to change the noise statistics. They're also going to be IID Gaussian. So that means that if we have a linear transformation that's also orthogonal, then we're going to kind of keep the statistics of our noisy input images, and we ought to be able to use those to create interesting images. And so this helps explain the failures. For example, when you rotate by 135 degrees, we're doing bilinear sampling. So we're averaging together pixels that are near each other by some weighted, we're taking a weighted combination of them. And this kind of messes with the variance of the resulting standard deviation. And also maybe more subtly, the noise is no longer independent. The noise at each pixel now is kind of correlated with the noise of its neighbors. And similarly, same thing happens when you do hybrid images. But this new understanding also allows us to expand the set of illusions we can make. For example, you might wonder why this illusion worked, where you could rotate this and get another image. Well, those rotation matrices are, or this operation of rotating the image can be framed as a permutation of the pixels. And permutations are orthogonal transformations. It's just a matrix. It's got a bunch of zeros and ones in it, and one per row. And that explains, why these different transformations work. These are all just instances of permutations of pixels. And so if you want, you can think of these successful techniques as kind of visual anagrams. We've, much like an anagram is rearrangements of letters in a word to get a new word, we can also change the appearance of an image after permuting its pixels. And it also raises questions, if it seems to work for one permutation matrix, what if we try others? So what about a square hinge? So from one perspective, this looks like an oil painting of a young lady. Well, what if we kind of break the image up into blocks and we rotate those blocks? Well, then we can create another image, and that other image can be an oil painting of an old woman. And in this case, our view function v just performs this special type of permutation. And another really interesting special case of this is our jigsaw puzzle. So this is a watercolor of a kitten. We see a kitten from one perspective, but really this image is made out of jigsaw pieces. And if we rearrange those jigsaw pieces, then we can create a watercolor of a puppy. And so you can create a puzzle that has two different solutions, one of which is a puppy, one of which is a kitten, and kind of 2-for-1 puzzle purchase. Here's a watercolor of a duck. Rearranging these puzzle pieces, you get a watercolor rabbit. Reuse the same puzzle in multiple different ways, so on. Oil painting of houseplants, an oil painting of a deer. And on our website, we have some of these puzzles. You can print them out and cut them out, and you gotta get a 2-for-1 puzzle. Okay, here's another kind of more aggressive permutation. We can just take the image, split it up into individual patches, permute those patches, go from a watercolor of a rabbit into a watercolor of a duck. And the interesting part of this is that the diffusion model is still able to work. We're like internally permuting the pixels, and it's still able to denoise the two different views and successfully generate these illusions. And another illusion that we were interested in addressing was this famous skew illusion. So you might have seen this famous painting called The Ambassadors. And if you view this from, you might have noticed it looks normal at first, but if you kind of look at it carefully, you'll see there's this weird artifact in the painting. And if you stand at this painting from just the right perspective, you'll see a skull. And so what if we just take a skew and represent that as a permutation? So we can kind of approximate this by kind of rolling each row up or down such that we end up skewing the image. And this allows us to create images that are inspired by that skull. From one perspective, it looks at an oil painting of a Tudor portrait. And then if we skew the image, we get an oil painting of a skull. And then one of the things we realized is that this should work with other orthogonal transformations besides permutations. So what if instead of permuting the pixels, we just negated the pixels? So if the pixels range from -1 to 1, then this would amount to flipping white to black, black to white, and so on. In that case, our transformation is this very simple function, which could be represented as kind of the identity matrix negated, satisfies the properties we need. And so we can use this to create illusions where we end up flipping the color, the intensity of the pixels. For example, this looks like, from one perspective, like a lithograph of a landscape. can invert the colors and get a lithograph of houseplants. Here's another one, a lithograph of a man. Invert the colors, get a lithograph of a woman. And you can also go invert it, the whole RGB color, an oil painting of a still life, flip the colors in an oil painting of a face. We can also try kind of really crazy orthogonal transformations. So this is just kind of a random transformation, and it still kind of works. You can say a painting of an old woman or a painting of a young lady from the two different perspectives of this orthogonal transformation. Photo of a rabbit, photo of a duck. And we also want to see if it's possible to run this in more than two views. So instead of just averaging the noise from two different perspectives, we can add a third one as well. It's harder to get these to work. The number of constraints on the pixels becomes a lot larger, but we have found some cases where we can do this. For example, there's an oil painting of houseplants from one perspective. From another, we get an oil painting of Elvis. I don't know if folks see it, but you kind of see his eyes here and here, his hair here. Here's another one. Now it's an oil painting of Einstein. His eyes here, here, and here, mustache here, and so on. Another one, from one perspective, looks like an oil painting of a waterfall. From another, you stare at it, you see it's an oil, look like an oil painting of a teddy bear. His nose is here. His ears are here. Finally, it looks like an oil painting of a rabbit. The ears are here, the eye is here, so on. And one thing that's interesting about this, we had, as I mentioned before in the Q&A, we had to use the a model called Deep Floyd to implement this. It's a diffusion model that operates on pixels. And interestingly, we couldn't get our model to work as well when we tried latent codes instead. So the most popular type of open source or open image generation method are these latent diffusion models. Like the most famous one is called stable diffusion. And these don't work because they represent the image in terms of a low-dimensional latent code. And these codes essentially encode patches of the image. And when you try to permute the patches, the content doesn't actually change with them. For example, this image of this puffin, when you permute, when you rotate it and you don't rotate the patches with it, you end up with this really funny looking image. That's the kind of result you get if you try the model with latent diffusion methods. And I want to point out two really great, closely related works that have also come out this year, and that actually appeared before ours. One is Illusion Diffusion by Matt Tancic. He has a Colab notebook online where they had a very similar method, and they posted these four images of rotation illusions where the images are rotated 90 degrees. They were using latent diffusion, so they end up with some of these artifacts, but you can see they have the same core idea. And secondly, there's a work called Diffusion Illusions, which was a CVPR demo from last year that has a very different approach. They use score distillation sampling, a really interesting technique that's been used a lot in 3D generation. They use that to generate different types of illusions, such as these illusions, where you can create images where you add different layers together and get different images as a result. Our model here seems to outperform both of these techniques that were developed independently on different generation tasks, such as when we have the model generate images using different prompts that are chosen either using an existing data set or in several other ways in the paper. And we found that they often have are kind of left with more artifacts, in part due to the fact that they rely on either these latent diffusion models or use score distillation sampling. And yeah, if you check out our website, you can find more of these illusions. We have a whole lot of them. And you can also try it out yourself. As I mentioned before, we have a Jupyter notebook online, and some people have created some really great Hugging Face spaces you can use as well. And I think I have a little bit of time. It looks like I'm right at the 30-minute mark. I'm happy to answer questions until Jimmy tells me that we should move on.
Yeah, the clown with the hook
Yes.
has not come onto the stage yet, but we do have a couple questions in there. Maybe I can prompt a few of these for you. Yash asks, is there a certain number of puzzle pieces that work best for the particular illusion that you were showing?
That's a great question. We haven't really explored it too much. It's actually kind of hard to create because you have to create puzzles that work in multiple different ways. It's actually kind of hard to do because the same pieces have to have multiple solutions. So we've only tried it a few different ways. I think that if you took the really extreme case where you had hundreds of puzzle pieces, it might actually be easier because it almost gives you like a palette where you can kind of choose whatever color you want at any pixel. And on the other hand, if you have too few pieces, there aren't that many total permutations. So yeah, it's kind of a trade-off there. If you only have if you have too many pieces, it can be really trivial. You just kind of like make anything you want by choosing the right color at the right location. If you have too many, becomes very easy in that there aren't that many total configurations. But in between, I think is sort of the sweet spot. And let's see. Thank you, Julianne. I'm happy to answer any questions you might have about the statistical properties. There's also a question about averaging 2 or 3 generated images. Yes, all of this is just simple averaging. You generate noise from multiple different images, you average them together. Or from multiple views, you just average them together. Is there an upper limit to the number of views you can properly do? I think in our paper we have some examples with 4 views, but it's at that point it becomes very hard to get it to work consistently. And then I see also in the webinar chat there were a few questions. Can a single image be used to generate more than 2 views using prompts from users? Yeah, so I guess we have an example of 3 views. I'm happy if I understand that question correctly. Yeah. So I mean, I think it becomes harder and harder as you have more. Can a model be trained to come up with the right pieces of the puzzle if a prompt is provided with specifications? Yeah, I think that'd be really interesting, though. I think you might need a very different learning technique to come up with the puzzle pieces than the diffusion model itself. And so it'd be really interesting to explore how you might put those things together. Can you use the model on combinations of multiple transformations? Actually, yes. I don't know if we have any on our website, but you can have like a puzzle that also looks different when you flip it, or some things of that form. You can kind of mix and match them. Finally, can we use 3D for both eyes? Yeah, I think 3D illusions would be really interesting. We haven't explored that. Oh, and also, yeah, Julianne, yeah, I agree. It's really interesting that these illusions from the 20s and later are actually being used in computer vision and also to try to come up with interesting test cases for images. I think it's really exciting to see these things that were originally just made for fun to actually lead to interesting results. So I think I'm probably out of time, so I'll stop there. Thank you, Jimmy, for inviting me, and thank you, everyone, for the really interesting questions.